Hello, my mathematical friends. Let's have another look at Heron's formula. This time we want a more geometrical proof. We did the classical way with a lot of algebra, but this time I want something that's more on the side of pure geometry. We will use results from two videos that I did previously. I will put the links in the description box. Incircle excircles part 1 and the second video, you guessed it, incircle excircles part 2. So go to the description box and follow the links to these two videos and watch them if you haven't already done so, or if you're not familiar with these incircle excircle results. Now let's have a look at Heron's formula again. Heron's formula tells us the area, we write it like this, square brackets ABC, of this triangle labeled in the classical way with little a, little b, little c are the sides opposite to those vertices. And Heron's formula is a very beautiful formula with a peculiar and interesting pattern to it, which we will examine. There it is. Look at this carefully. We have these factors p minus a, p minus b, and p minus c, where p is the semi-perimeter. Where have we seen these factors? Well, we've already seen these things in our videos, in the tangent segments. The tangent segments to the excircle and the incircle were all of the form p minus a, p minus b, and p minus c, going all around those circles. We've calculated the lengths of those tangents and we got that. But then there's also the area of ABC in terms of semi-perimeter and radii of incircle and excircle, and we had these beautiful expressions RP, RAP minus A like this, RB P minus B like this, and RCP minus B, P minus C. And when you look at this, well, it rings a bell. Like, notice that these factors are the factors that appear in Heron's formula. So the immediate light goes on in your mind and you say, hey, wait a minute, maybe I can use excircles and incircles to prove Heron's formula in some way, because it's all constructed from these things that we have derived from incircles and excircle. And the answer is yes, you can, of course. And in fact, this is going to be a much more geometrically satisfying proof, relying on geometrical principles like similar triangles and so on, and some other things. And our results about tangent, symmetry of tangents to a circle, like we did in video 1 of incircle, excircle. And okay, and it doesn't use mountains of algebra like in the classical proof. That can be daunting and intimidating, and but it has a little bit of algebra, this proof, but not that much of it. Mostly it's geometrical reasoning. So I think this is a great way to prove Heron's formula. It is, of course, superior to the way I showed you before, but it takes some doing. We had to hack through all those properties in the two previous videos before we could get to this point. The strategy of the proof will be like this. We're going to get a pair of similar triangles and the relationships from those similar triangles, and then we will look for another pair of similar triangles with relationship, and that should be enough to derive Heron's formula. So here is our triangle ABC. I have not labeled the sides with little a, little b, little c. You can figure that out. The figure gets too cluttered if I put too many symbols in it. But we have our triangle ABC. We have our incircle here in red. And we have the excircle. I've chosen the B excircle corresponding to side B here. So we have a pair. We have the incircle and one excircle. And I've deleted most of the tangent points, and I've kept only the ones we need. So for my particular demonstration, I'll need this one, a tangent point alongside C, and I'll need this tangent point. So an inner incircle tangent point on side C and an excircle tangent point on side C. That's kind of an interesting pattern, and I'm sure that this pattern extends itself all over the place if I draw more of these circles. But let's see if we can find the first pair of similar triangles. Of course we can. Here they are. Let's have a look. So the big triangle here, all along like this triangle is obviously similar to this triangle. Now I have to prove some things about this, because how do we know that the line from IB to center here to B goes through I? How do we know that? See, if it doesn't go through I here, if it does not go through I, then this is not true. Okay, these triangles are actually, they're not similar at all, right? So we have to first prove that. Okay, so let's write that down. So we want to argue that point I, the center of this incircle, is on this line BI. Well, you know that from tangent symmetry, this line here bisects this angle here, okay, and it goes through the center of the circle, all right, because of tangent symmetry. We showed that in video 1 of incircle, excircle. But I have the same situation here. These long lines here and here, they are also tangent lines, and so this bisector line must also go through IB. So the bisector line, this is how I can phrase it, bisector of angle CBA, that's this angle here, bisector of angle CBA must go through I and IB by tangent symmetry, okay, by the tangent symmetry. Now, also from what we learned before, this angle is 90 degrees and this angle is 90 degrees by tangent perpendicular to radius. These triangles have 90-degree angles. So angle ITCB is equal to angle IBSCB, and that's 90 degrees. And so the two triangles share in common two angles, and that means that they're similar. So let's write this down. So therefore we have enough information now. Triangle, the big one, let's start with IBSCB is similar to the little triangle ITCB, like that. And if they're similar, well, there must be similarity relationships, yes? Okay, I deleted some stuff. Let's go back up here, and so I can have the figure. What's the length of this side here? This side is RA, or RB, sorry, because we're circle B, excircle. And this, we usually give the incircle just plain R. So we can begin. Okay, RB. Here it's like really clear which side correspond to what side, so it's really easy to write down the relationship. So this whole thing from here to here, if you recall from video 2, this length was video about incircle, excircle 2. This is P, and this over here, does anybody remember? This is P minus B. P, well, okay, I don't need to draw this arrow, just P minus B. So this length P minus B, it corresponds to the big one, the big side of the big triangle. All right, so we have our first similar triangle relationship, P minus B, like this. Okay, I'll highlight this. This is very nice. Okay, let's keep that in mind. That was the first one. We need another one, and then just some fancy magic, and we're done. Now we have to find a pair of similar triangles, a second pair of similar triangles, something different from what we found above. So here in our main figure, there has to be another pair of similar triangles, and we got to look carefully. And if you have a good imagination, you can see them. Here they are. Let me get some color and show you where they are. Well, you have this one bigger one here, like this. And you have this here smaller one over here. Now, they look similar to the eye a little bit, but we want to prove that they're similar. So that'll take a little bit of work. And it's actually very interesting, this proof. You'll see. There, I moved things around so I have more room. Let's look at this. This angle here plus this angle here must be 180 degrees, yes? Those two angles are supplementary. Very good, very good. Now, let's call one of these things X and the other Y. So let's call this unknown angle X here. And this one, we don't know what that is. That's also Y. So we'll call that Y. And our job is to find something about X and Y. We'll see if these three angles are the same or not. So the first thing we can notice is that, let me draw this. This is tangents, two tangents, okay? And the line AI bisects this angle. So AI bisects angle TCAC. And likewise here, AIB bisects angle SCAC. How do I know that? Because we did that in video 1 of incircle and excircle. We showed that tangent symmetry gives this property that the line going from the point to the center bisects the angle between the two tangents. Okay, so this is known. So we can now write these relationships like this. X is 1/2 this big angle here, TCAC. Y is 1/2 of that angle, and X is 1/2 of this angle here. Let's see if I can color it. This angle here, X is 1/2 of that. All right, that's getting messy. Let's restart X and Y. Great, so let's plug these things in. We have 2y plus 2x is 180 degrees. So we've taken this and plugged it into there. And y plus x is 90. So these angles are complementary. So in other words, if this is x, this must be y, because it has to add up to 90 degrees. Why 90 here? Because tangent is perpendicular to radius. Remember, tangent here is perpendicular to radius at the point of tangency. And again, here we have tangent perpendicular radius. So this angle here, I don't have much room, so I'll write it outside. This must be x. So in fact, these three angles are the same, and these two triangles are similar. So let me write that down carefully. Triangle ITCA is similar to ASCIB, and I'm careful to match. I matches with angle X, TC is at angle, the perpendicular angle, and A matches with Y, yes, and same here. Now, for the bigger triangle, A matches with X, IB matches with Y, and SC is the 90 degree angle. So I have my proof now that these two things are similar, and I can do just like before. I can write down some relationships. So in order to do that, let's clean this up a bit. X, okay, let's get black. This is X. Y, this is Y, this is X, this is 90, this is 90. I need the lengths of these things now. So this length is the radius RB. RB, we have the B excircle, RB. And this length is R, the incircle radius. And if you remember from the videos, this is P minus A, this length here. Let me highlight this. This length here is P minus A, and this length here is P minus C. So now let's set everything up. This is the big triangle, and this one here is the small one. We'll take the sides corresponding to angles X and Y. So X corresponds with RB. Y corresponds to P minus C. And this is going to be equal to, do the same for the little triangle if you look carefully. X here, this is angle X, corresponds to this side here, P minus A. And the Y angle corresponds to the side length R. And there we have it, our second similar triangle relationship, and this should be sufficient to derive Heron's formula. So we just have a little bit of manipulation to do and a tiny bit of magic to throw in that I will show you. It's very pretty, and we'll have Heron's formula. Now we've reached the final step of this proof. Let us recall the two relationships we got by studying pairs of similar triangles. From the first pair, we have equation 1. RB over R is P over P minus B. And from the second pair of similar triangles, we got this one. So what should we do? Well, we start with 1 and we solve for RB. We want to get rid of RB. And what do we have then is RB is equal to RP over P minus B. So we plug this in 2. Plug in equation 2. And what do we get? We get this. And now let's rearrange things and bring everything to the numerator so that it looks more like Heron's formula. I bet you feel now that you're very, very close to the final result. Well, what we need to do is multiply both sides. So we multiply both sides by P, by the semi-perimeter P, and we get R squared P squared is P minus A, P minus B times P minus C. Now, here is where I said there's just a little bit of magic. And if you remember, the formula for area in terms of incircle was RP. And so therefore this is area squared. ABC squared is P minus A, P minus B, P minus C. I like writing it. It's really fun formula. Okay, one more time. ABC is square root all of this P minus A, P minus B, finally P minus C, big square root, and there we have it. Heron's formula proved by geometry with just a little bit of algebra at the end. It's very, very beautiful, this proof. It contains many, many techniques that everyone should know, especially if you are a competitor in Olympiads and things like that. This is very good training. And I will give you an exercise to do to help you with that training. So here's an exercise to help train your geometrical insight into all the different techniques that we used here. I have the same sort of figure, except now I have the IA excircle, a different excircle, the same triangle, the same incircle, but now it's the A excircle, and I want you to repeat the same derivation. So do same derivation. Okay, you find the triangle, find the similar triangle pairs. So you find the pairs of similar triangles and then prove Heron's theorem, prove Heron's formula, if you'd rather say formula. Okay, and this is a great exercise because you have to think like it's the same thing, but it's not the same. It's a different orientation. This is a really good practice for you. And there may be many ways, well, there may be more than one way to do this. Like there could be some other sets of triangles that we didn't examine. Notice that I have put all of the tangent points just in case you need all of them or some of them. So are different kind of tangent points from the ones we used above. Okay, and so you copy this figure, screenshot it, print it out, cut and paste it somehow, and put it in your notebook and get to work on it. Well, I hope that you like this. This has been an amazing experience, finding a geometrical proof of Heron's formula that's very elegant. I've seen some proofs that I really didn't like. For example, there's a cosine law proof which relies on factoring some big polynomial, and I think that really is not an insightful proof. It's not fun at all. But this one is really good, really insightful, and really interesting. So as always, click like, subscribe, leave a comment in the comments. Tell me what you think. Tell me which proof do you like better? Do you like the classic proof with all the algebra and Pythagoras' law, or this excircle proof that I just showed you? Let me know in the comments. And as always, I will see you next time.